And of course, I'm holding lecture remotely today because of little emergency that I have, which is actually under control. So, and I think I sent a message via the announcement section that today's lecture will actually be held remotely. Of course, I can assure you we're going to return to an in-person teaching tomorrow. Okay, so before I go into today's lecture, I'm going to say this week is actually a week of midterm 2. And of course, the way the exam was conducted in midterm 1 is the way I'm also going to conduct it in midterm 2. So where I'm going to open the exam, I think July 14 all the way to 15. Okay, but the instruction about how the midterm is going to be, of course, you're basically going to receive, check the announcement section today for detail. Okay, so the focus in the midterm 2 is basically going to be what we did in week 3, 4, and 5. Of course, week 5 is last week. So, which means all assignment solutions. I have instructed my TA to upload all assignment solutions if she has not done that. So I'm going to say that again. The midterm 2, we focus on what we did in week 3, 4, and 5. Of course, 5 is last week, right? So week 3, 4, and 5. So which means what we're going to be doing this week will not be part of midterm 2. I'm going to say this again, the midterm 2, we only cover what we did in week 3, 4, and 5. I'm going to say that again. The midterm 2, we only cover what you did in week 3, 4, and 5. When I say week 3, 4, and 5, the 5 is last week. So what you're actually going to do this week will not feature in midterm 2. On the final note, I'm going to say this. The midterm 2 area of focus is going to be week 3, 4, and 5. Okay, what we are going to do now, what we are going to do this week will not be part of midterm 2. And of course, our assignment solutions, assignment 3 solution, assignment 4 solution, assignment 5. Let me see. Not assignment 5. Yeah, assignment 5. So 3, 4, 5. They are very, very crucial. But just like what I did before, I'm actually going to release practice questions. And of course, this time around, there's not going to be multiple choice. Okay, it's just going to be short answer questions, the midterm 2 this time around. So more information about that would be expected today. Please make sure you check announcement section for detail. Okay, so what we want to do today, what we want to do this week will not be part of midterm 2. Okay, on the final note, what we are going to do this week will not be part of midterm 2. Like I said, the midterm 2, we only focus on what we did in week 3, week 4, and week 5. Okay, and when I say week 5, I mean last week. Last week was week 5. Okay, so I want to welcome everyone to my lecture today. The title is Jointly Distributed Random Variables. And of course, the jointly distributed random variable is basically going to be, chapter 5. And let me also say this. If you are talking about jointly distributed random variables, what we've been doing, we've been focusing on a single variable. Okay, at times you can have a situation where the statistician or the analyst, may actually be interested okay, in looking, in observing some, more than, more two or more measurements that occur, okay, simultaneously. The one we've been focusing on is basically, one measurement. What of in a situation where we're actually looking at the simultaneous occurrence of more than two observable measurement. Of course, we're actually going to be talking about the idea of jointly distributed random variables. This can be found in chapter 5 of the recommended textbook. Okay, so I'm actually going to go into the outline. So in the outline today, I'm going to walk you through, situation where, you know, uh, starting from two variables, right? Two variables, maybe X is discrete, Y is discrete. Okay. When X is discrete and Y is discrete, of course, they're actually going to be jointly, distributed. So the name of that distribution is actually going to be called joint probability mass function. Don't forget the other time when we're dealing with a discrete random variable, we're actually calling the probability function probability mass function. Okay, so this time around, you have X that is discrete, and you have Y that is also discrete in nature, and they are distributed jointly. Okay, the name of that function is going to be called joint probability mass function. Now, what of in a situation where X is continuous and Y is continuous, okay, and they are distributed jointly, okay, the name of that probability function will be called joint probability density function. You remember the other time when I was walking you through, continuous random variable, okay, if I want to obtain a probability of a continuous random variable, I'm actually need to integrate a function called probability density function. Okay, but in a situation where we're looking at one measurement at a time, I mean, more than, we're looking at more than one measurement. Okay, if we're looking at more than one measurement, and this measurement actually, they are continuous in nature. Okay, so we actually can have a way to have a probability distribution that connects them together, and that will be called joint probability density function. And for us, I'm actually going to walk you through the application as well. Okay, so I want you to take a look at what I'm displaying now. Okay, this is a joint probability mass function. Okay, like I said, we have X and Y. X and Y, they are discrete random variable. Okay, now, and let me tell you this. Discrete random variable, what do I mean this time around? When I want to talk about the X and Y now, okay, X is likely going to be, dichotomized, like it's basically going to have levels. And Y, we're also going to have levels in such a way that we can actually represent the two variables in form of a contingency table where we can cross tabulate. You get what I mean? X as levels, Y as levels. Okay, I can give you an example now. Okay, you may want to look at the what if you want to look at the, you're talking about level, level of income, okay, and educational attainment. Educational attainment, okay? If I call educational attainment X and I call level of income Y, maybe probably what I want to say is I'm trying to say if a relationship exists between the educational attainment, like the educational qualification that I have, how does that actually related to the level of income? In that situation, X and Y, they're basically going to have levels. Okay. Now, if they have levels, it means you're actually observing more than one measurement at a time. If you take a look at what I have here, okay, if you take a look at this guy, I want to find the probability of XY. That's a joint probability, joint, because I'm having more than one variable. Okay, when that probability of X comma Y basically going to be equal to, well, the probability of S equal to S and Y equal to Y. Maybe I'm interested in what is the frequency of the numbers of participants that are high school graduates and they have less than $40,000. Take a look at that. That's a joint. Okay. Now, uh, you know, when we actually have a now that is actually a set consisting of PI of X and Y. And what we're actually seeking for is a probability of X, Y, X comma Y, which is joint. And don't forget the X and Y lies in the set A. Then automatically we're actually going to be looking at the idea of a two sum. Oh my God, why do I have a two sum? The other time when I was only focusing on one variable, we only have a single sum. Okay, we only have one sum. But right now, because the focus is on two variables, it's going to be two sums. If the focus is on three variables, it's going to be three sums. I need you to take note of that. So what we're doing now, I'm only giving you the example of X and Y, when you have two events that occur simultaneously. Okay, we can have three events, four events, and so on like that occur simultaneously. So take a look at all of that. Okay, now another thing that I want you to take note now is, do you know that when you are giving a joint probability mass function, where X follow discrete, Y follow discrete, and we are at the two events are actually modeled, by a function that we call, a joint probability mass function. Let's say, for instance, I'm interested in only one variable at a time. For instance, if I'm interested in random variable X, and I have a joint X and Y, and the law is going to tell me what I'm going to do. I'm going to sum the joint over the range of the variable I'm not interested in. What am I interested in? I'm interested in the variable, in a function that has to do with X. Don't forget, what do I have? What I actually have is this guy. That's a joint, right? I got a joint, right? I got a joint PMF. Okay, that's a joint PMF. The joint probability mass function. It's just like I situation where I have a function, that's actually, that is distributed according to the level of income and educational attainment. And I say, okay, you know what? I only need variable that has to do with the educational attainment, okay, which is this guy here. If that is what I'm interested in, then I'm actually going to sum the joint with respect to the variable I'm not interested in. If I'm interested in X, then I'm actually going to sum that joint over the range of the variable I'm not interested in. That is what I mean. Take a look at this one as well. I'm interested in Y now. I'm interested in a function of Y now. So if I'm interested in Y, then it means I'm not interested in X. Then if I want to figure out the function of Y using the statistical architecture of the joint, what I'm going to do, I'm actually going to sum the joint over the range of the variable I'm not interested in. Now, what do we now call these two? We now call them the marginal. That's what we call them. The marginal probability mass function. That is what we call them. It's like that's a way of going backward, going back to what we've done before. We've been focusing on just one variable at a time. I need someone to confirm again if you are hearing me clearly. Is everyone hearing me clearly?
Yeah, we're able to do that.
Okay, good job. Thanks for confirming that. Now, I want to walk you through an example now. When we're talking about joint, I told you the other time, we're focusing on the situation where we are actually observing measurement that's actually occur simultaneously, where we have two or more measurements occurring, simultaneously. We're no longer focusing on one. Okay, I gave you some example here, but you know what? I will quickly go, because of my time, I will quickly go into an example that has to do with the joint probability mass function situation where, one variable is discrete and another variable is also discrete. Let's take a look at it from this example here. Now, we are interested in the effect of seatbelt use on saving lives. If we consider the following random variable x1 and x2, take a look at that, x1 and x2, okay? I can say x1 and x2, I can say x and y, okay? I can use whatever variable, whatever alphabet that I actually want to use, but I'm defining them now that we got more than one variable at a time. Take a look at that. Now, if you take a look at the first one has levels. But when I mean by levels, okay, the numbers of levels here is 2. I'm still talking about x1. Now, when you take a look at x1, x1 equal to 0 if a child survive, and x1 equal to 1 if the child did not survive. Then what is the x2? Okay, x2, oh my God, s2 has 3 levels. Here, this is 2 levels. This is 3 levels. It doesn't really matter. You can have more than one variable, and each of these variable may has a different levels. They could have the same levels, but they can also have different levels. Okay, when you take a look at the second one now, we got 3 levels. When x2 equal to 0, if no seed bet is used. Okay, no seed bet, x2 equal to 1. If other bet use, x2 equal to 2. If child seat, use. Take a look at all of that. Okay, now if I have this now, of course, it's going to be discrete. Why is it discrete? Of course, the state space can be counted. It's a discrete because the state space can be counted. You got 0, 1 for the first variable, right? And what is the state space for the second variable is 0, 1, 2. That's a discrete. Okay, now take a look at this. Oh my God. This is a contingency table that I just talked about. You are given all this probability. Take a look at this. The x1 has a 0, 1 level. Can you see it? Can you see that? And x2 has a 0, 1, 2. Take a look at that. Now, do you know that what you have here, they are the joint probability. We call them joint probability. The joint probability, I mean the probability of x1 comma x2, which is more or less the same thing as this guy, the probability of x1 equal to x1, okay, comma, x2 equal to realized value x2. Okay, now what am I trying to talk about? Well, we take a look at this guy now. Oh my God, what that guy means is the probability of x1 equal to 0 and x2 equal to 0. Take a look at that. That is what that guy means. Okay, and when I say x1 equal to 0, s2 equal to 0, what does that mean in the real sense? If you want to go back here, I'm talking about this guy now. Okay, now what is a joint probability? Okay, a child survive and no bets, and no bets. That's a joint for that. That's exactly what I mean. Okay, so when you take a look at this table now, okay, it consists of, that's a joint probability, the possible joint probability, okay, that we can have, situation where, X1 has two levels. Don't forget, this guy has two levels and this guy has three levels. The possible numbers of cells I'm actually going to have is going to be 3 times 3. That's going to be 6. Okay, where is the 6? 1, 2, 3, 4, 5, 6. Take a look at that. That is a possible number of combination we're going to have. I mean, a possible combination. Now, if I now want to find the, you know, if I basically want to find what I call the marginal now, what am I going to do? If I need a marginal, take a look at this guy. That guy is the probability of x2 equal to 0. That's a marginal. The marginal, what have I done? Oh my God, what I've done? I basically, using the idea of x1 comma x2, and I'm summing over the range of x1, starting from 0 to 1. Take a look at the formula that I'm actually using now, which is summing this guy. Take a look at that. Okay, over the state space of x1, because I'm interested in x2, I'm actually going to sum my joints, okay, in terms of the variable I'm not interested in. Take a look at that. It's 0.55 now. Okay, it's representing a marginal probability of x2 equal to 0. If you take a look at this guy now, that is for x2 equal to 1, which is just adding this to that. That's super easy, adding that. That's what it means, right? And the last one, that is for when S2 equal to 2, just adding those two guys, getting this guy. What if in a situation where I'm interested in just X1, okay, I'm interested in probability of S1 equal to 0. Oh my God, I want to get the probability of X1 equal to 0. Can somebody tell me for extra credit what is going to be the value for the probability of X1 equal to 0? Can somebody tell me?
0.76.
It's 0.76. Look at me. Good job. That's going to be 0.76. Okay, so which means the formula that I've used now, when x1, it means I actually use the probability of x1 comma x2, and this time around, I'm actually going to sum using the variable x2 from 0 to 2, which is adding all of that. Okay, that's getting marginal. Take a look at all of that. That's getting marginal. Okay, and if I want to get the probability of x2 equal to 1, okay, of course, it's basically going to be this guy, okay, using the same formula. Okay, when you are given, when you're working with a joint or probability, function, you actually, sometimes you're going to be working with a table, a contingency table like this. Okay, I think I just walk you through how to figure out, the marginal probability from a given contingency table. Okay, so this is what I've been doing, it's like, okay, I want to find the probability of x1 equal to 0 and x2 equal to 2. That would be 0.24, which is good. Basically this guy. Okay, this is when s1 equal to 0, and this is for when s2 equal to 2. That corresponds to 0.24. That's a joint. Take a look at that. That's a joint occurrence of an event. Okay, now I'm going to move right now. And of course, I just walk you through the other one. Now, is there anyone who want to ask question before I move to the joint probability density function? Is there anyone who need clarification now? Okay, if you are all good, if you understand what I just explained, I need you to say yes, or you type you chat with me saying yes, or you give me a thumbs up if you really understand what I've explained about the probability, the joint probability mass function. Okay, that means you understand that, but if you don't understand that, please make sure you ask question. Do not hide your feelings. Now we want to go into situation now. Okay, we basically want to go uh, into situation where X and Y follow, they are continuous random variable. S is continuous, Y is continuous. Okay, now this is what we're seeking. Don't forget the other time when I was walking you through the disk, the one variable situation. Okay, if I'm actually seeking the probability of a particular random variable, and if that variable is continuous, okay, if that variable is continuous, oh my God, what I'm actually going to do is to integrate, the probability density function. But right now, I'm focusing on two variables, x, y. Then I'm actually going to have two integrals. Take a look at that. Integrals, integral, f of x, y, ds, dy, because I got two variables. What if in a situation where the numbers of variables I got is three, then I'm actually going to have three integrals. So what determines the numbers of integrals that I'm actually going to get depends on the numbers of variables I'm actually looking at a time. That's what I mean. Of course, we expect each variable to have a state space. Oh my God, X actually have a state space between A and B, and Y has a state space between C and D. Okay, at time, X and Y, they could have the same state space, and they could also have a different state space, just like what I just walked you through under the discrete, where we talk about two variables. One has two levels, and the other one has three levels. Take a look at all of that. So if I'm now seeking to obtain the probability of xy, what do I mean by that? That's a joint occurrence. The probability of the joint occurrence. Oh my God, I'm going to use this as an example now. Okay, maybe you try to go into a particular bank. Okay, you know the a bank has two facilities. They have a drive-in facility, and they also have a walk-in facility. Okay, let me say walk-in. Okay, you can walk in, you can drive in. Okay, now if x represent the proportion of time the walk-in facility is being used, and y represents the proportion of time the drive-in facility is used. Of course, in a particular bank, they're basically going to be experiencing these two at the same time. Oh my God, why some are walking in into the backing hall, some are driving in. Take a look at that. Those are the two events that can occur simultaneously. And mathematicians now have a way, to actually, create a probability function for them. And that probability function can actually be used to figure out any statistical inference that we actually want to figure out. Okay, because the idea of the joint distribution will enable us to figure out, is there any relationship between them, or there's no relationship at all. And that will lead us to something that I'm actually going to call, is x greater than y, or is x less than y. In this case now, is the number of customers, or, using, the driving facility. Is it more than the working facility? Or I can say, what is the probability of the proportion of time the working facility is used, given that the driving facility is something. You know, series of questions like that can start coming in. So which means with the idea of a joint probability distribution, that will give us opportunity to be able to answer, that kind of questions. Okay, we don't just do math. There's a reason why we do math. We do math to apply math. Okay, now um I'm gonna go to something else. Oh my God. Remember what I walked you through the other time when we add the probability, the joint probability mass function when you have a joint P of x, y, and we basically interested in a function of x. You know what we did, right? In a discrete case, if I'm interested in x, right? I'm actually going to sum, okay, the joint over the range that I'm not interested in. If I'm working with a continuous right now, okay, with a continuous right now, I got the f of x, y, but I'm interested in f of s, okay. If I'm interested in f of s, I'm not interested in y. I'm interested in a function of x, then it means I'm basically going to integrate, okay, the joint with a respect to the variable I'm not interested in. Because I'm not interested in y, then I'm going to perform my antiderivative with respect to y. So with this now, this is a marginal function of x. The same thing also applicable to y. I'm interested in y right here. Then I'm actually going to integrate my joint PDF with respect to x. Look at that, with respect to x. And I'm actually going to use the range of x in my integration. Okay, basically going to integrate, with the respect of the variable I'm not interested in. Okay, so this is how we figure out the marginal. Okay, this is how we figure out how the marginal probability density function. Okay, so I want to move now. Oh my God, we want to go into example now. Take a look at this back example. We all go to banks, right? Okay, a bank operates a driving facility and a walk-off facility, okay? And X represent the proportion of time the drive-in is used. And Y represent the proportion of time the walk-up is used. I want to believe it's not going to be 100% of customers, okay, in this bank that is basically going to make use of a drive-in, okay, and not 100% that will make use of a walk-up. But you know what mathematician has done? The mathematician have really looked at the situation, okay, the arrival, the way these two facilities have been used, and they are able to formulate a probability of the joint occurrence of these two events to be 6/5 into x plus y squared. And where the range of x here is going from 0 to 1, the y also go from 0 to 1. That is not surprising. You know why that is not surprising? That's going to go from 0% to 100%. Okay. Now x, therefore, the proportion of time the drive-in is used is going to be lie between 0 and 1. And the proportion of time the walk-up is used going to be between 0 and 1 as well. And let me tell you this. Just like the same way that we investigate the validity of, of a PDF in one single measurement and the validity of a PMF in one single measurement, we can also do the same, when we're, when we're dealing with the joints. Take a look at that. If I have this guy now, I can show that it's integrated to 1. If I want to show that, you know what I'm going to do? I'm actually going to use the range of, 0 to 1, 0 to 1, okay, 6/5 x plus y squared dx, the y, okay? I must be able to show that that guy equal to 1. If it is equal to 1, you know what that means? Then it means that's a valid joint PDF. So you've all first integrate to, with respect to x, you're going to use the range of 0, 1. Then after which you're going to integrate with respect to y. Okay, so I needed to revisit your calculus knowledge. Okay, now we can now, I told you the other time, the idea of, the joint or PDF or the PMF will enable us to be able to investigate whether there's a relationship between the two variables. If you take a look at this guy here, we want to say, is there any relationship between the proportion of time the driving facility is used in a bank and the proportion of time the walk-off facility is used? Is it going to be more of this, more of that, or less of this, or less of that, or more of this, less of that? We basically want to know without having a probability joint, function. There's no way we will be able to do that. And you know what? If I want to know whether they are independent or not, it means I basically want to look at their joint variability. Joint variability. It means I'm actually going to talk about, looking at the autocovariance. Okay. And when the autocovariance is standardized, it becomes a correlation. I know you've heard about correlation before, right? The correlation is when you're trying to look at the relationship between two variables. Is it going to be positive? Is it going to be negative? Or there's no relationship whatsoever? Okay. So without actually, having a joint, variability, or, the joint, having the joint probability function, there is no way we will be able to investigate the relationship. Now, when you take a look at what I have now, I'm talking about independence. You know what I mean by independent? Of course, if you go by the idea of the probability that we've done before, okay, you'll remember, oh my God, the probability of A intersection B equal to the probability of A multiplied by probability of B. We've done this before. We're actually going to use that idea here, okay? When I have a joint PMF, if I can express a joint PMF as the product of the marginals, then it means X and Y are independent. If X and Y are independent, you know what that means. Independent means they don't have relationship. That's what it means. No relationship. That's what we mean by independent. And for a continuous case, we don't have that. So which means in a continuous case, of course, I just show you how to figure out the joint, the marginal, whether you are given a joint probability mass function or a joint probability density function. I just walk you through how to, compute the marginals. And if you are asked to investigate whether two variables are independent, or what you just need to show is that when you multiply their marginal probability, does it give us the joint? That's all you're gonna, that is all what you're just gonna do. Okay, even though we have other ways to show that, which I'm still gonna let you know. Okay, now I want us to go into conditional probability now. Okay, conditional probability now. Of course, we're actually going to use the idea that we use in the probability the other time, the occurrence of a particular event depending on another event. We're also going to have, take a look at this, f of y given s. That's a conditional function. It's basically going to be the ratio of the joint to the marginal. Do you remember this guy? The probability of A, given B, which is going to be the probability of A intersection B divided by probability of B. That is exactly what we are actually using here. We're using that idea here now. That's a conditional. I mean, basically want to figure out, well, if the walk-off, if I know the proportion of time the walk-off facility is used, okay, can I calculate the proportion of time the walk, the drive-in facility is going to be used? Or I want to go into politics. If X represent the proportion of voters that voted for a Republican candidate in 2016, and Y is the proportion of voters that voted for Republican candidates in the United States in 2020, okay, then I can figure out what is, what is f of Y given S. Just like if I know the proportion of voters that voted for a Republican candidate in 2016, can I actually figure out, what is going to be the proportion of voters that will vote for the Republican candidates in 2020? That's a conditional probability. Take a look at all of that. Okay, now I want to walk you through an example now. I need you to take a look at this. Let the joints of two random variable X and Y be given as what I'm trying to show you now. Oh my God, take a look at the support of X and the support of Y. Okay, the state space of X is 0 to 2 and the Y is 0 to 1. Take a look at that. And you know what I asked you to do? Oh my God, can you try and figure out this guy and this guy? How do I get the results? Okay, what I'm trying to tell the world is if I basically want to get the f of X, I'm actually going to integrate the joint. Oh my God, the joint over the range of Y that I'm not interested in, but I'm interested in that of X. So what am I going to do now? My f of X is basically going to be 0 to 1, 1 over 6 into X plus 4Y, okay, the Y. That's exactly what I'm going to do. I'm only going to integrate that guy out. Don't forget integrating that guy out, S is constant, okay? So, and, so if you want to do that, let me walk you through one example. You're basically going to do the rest. So let me just take the picture of this so I can share my whiteboard. I'm actually going to share my whiteboard now. Okay, what I really want to walk you through how to do that. Can you all confirm if you can see my whiteboard? Can you see my whiteboard?
There's a white screen.
Exactly. So that's my whiteboard. Thank you so much. Now, you're giving f of xy, right? Equal 1 over 6 into x plus 4y. Okay, and the range, you're giving the range of X to be 0 to 2, you're giving the range of Y to be 0 to 1. Can you all confirm what I'm writing on my whiteboard?
Yep.
Yeah.
Okay, thank you so much. Thank you for confirming that. And you know what I'm interested in now? Oh my God, I'm interested in f of X. Okay, so I'm trying to say now, I'm actually going to integrate this guy with the respect to the variable I'm not interested in. Okay, so right now, 1 over 6, 0 to 1, X plus 4Y. Okay, the Y. So this is going to be 1 over 6. I'm actually going to have XY plus 4Y squared over 2, okay, 0 to 1. So 1 over 6 into xy, okay, plus 2y squared, okay, 0 to 1. Take a look at that guy now. When you plug in 1, okay, when you plug in 1, I'm actually going to have, okay, you don't forget you're plugging in 1 to replace y. Y, don't forget you integrated with the respect to y. So when you plug in 1 now, that's going to be x, okay, plus, okay, 2. Okay, look at that. That was how I got the f of x to be equal to 1 over 6 into x plus 2. That's an f of x. Okay, you're also going to do the same. I'm going to stop my share now. I'm actually going to share, give me 1 second. Okay, now take a look at, that was how we actually obtain this guy here. When you follow that up and you do that of the f of y, that is what you're going to get. Oh my God, when you have f of s and f of y, it should be very, very easy for you to get the f of s given y. Oh my God, take a look at the formula here. Okay, when you take a look at the formula here, the f of xy is this guy you've been given. Okay, so this what you're doing, that's why you have this guy here, right? Okay, what is f of y? The one you just compute is right here. All we just need to do is to simplify, and that is going to lead you to that. Take a look at that guy now. The conditional function will be very, very easy the moment you have your marginals. Now, take a look at this guy. We can also have f of y given x. The same time we have f of x given y. They are not the same. The f of y given x is basically going to be the joint, okay, divided by f of x. Okay, and take a look at this guy. Okay, the f of x given y, okay, is basically going to be f of xy divided by f of y. Take a look at that guy now. Okay, now another thing you may want to find is, take a look at this. Take a look at this guy. He said, now that we've obtained the conditional of s given y, okay, now we can now find the probability that x less or equal to 1, given that y equal to 1 over 2. You know what you're going to do? Given that y equal to 1 over 2, you first plug in where you say y, plug in 1 over 2. That's exactly what I'm doing here. Anywhere I see y, I plug in 1 over 2. And after plugging in 1 over 2, then I simplify. I'm basically going to have this guy. When I have this guy now, then I can now find the probability. You know, what I want to find is the probability of x less or equal to 1, given that y equal to half. Since you're working with s given y, it means I'm actually going to use a function, a conditional function of s given y, which is the one that I've derived here. Look at that. And as I plug in y equal to half, then that is what I'm actually going to use to find the probability of s less or equal to 1. Take it. That's what I'm doing here. Give me 1 second. Okay, take a look at this now. As you know, look at what I'm finding. Take it that, you know, it means I generate this function here. Okay, and how do I generate that function? Using the conditional, using the formation here. I first plug in y equal to half, which is what I'm doing here, and that led to this guy. And after that, then I will be able to find the probability of s less or equal to 1, which is exactly what I'm doing now. Oh my God, that is my result for that one. Take a look at that. Any question? Any question on that? That's super easy, right? Okay. If there's no question, I'm going to go to the next one. Take a look at this. Oh my God, we do this most of the time. Let x and y denote the proportion of two different chemicals in a sample mixture of chemicals used as an insecticide. Suppose x and y have a joint probability density function given. Take a look at this. That's a situation where the joint can be a constant function, just two. And I don't need to pay attention to this. We got 3, x lie between 0 and 1, y lie between 0 and 1, and x plus y lie between 0 and 1. Take a look at all of that. And this is what you want to find. Find the marginal density function for x and y. Okay. Okay. You want to find the marginal for x and y. This is what you're going to use. You see, it's 0 to 1 minus s. Why? Take a look at this. If you solve that, okay. If you solve for y, that will be 1 minus x. If you solve for x, 1 minus y. That was why you also have this guy. It's a marginal. Take a look at that. Okay. Now, the moment you have your marginal, you can investigate are x and y independent by multiplying this by this. If you multiply this by that, okay, check the final result. Does it give this guy? If that gives the joint, then it means x and y are independent. But right now, what do you see? They are not, because we don't expect the product here to be. And that was exactly what I'm doing here. Oh my God, that is exactly what I'm doing there. Because of that, I'm not going to say that. I'm going to say they are not independent. They are not independent, means they got relationship. Finally, I can find the probability of s greater than half given y equal to 1 over 4. But all what I just first need to do, I need f of s given y. which is going to be f of xy divided by f of y. Then I'm going to plug in 1 over 4 force for y. Then greater than s greater than half, we're going to go half go to 1 because the range actually end in 1, and that's going to give me 2 over 3. Take a look at that. Oh my God, that is going to be the end of my lecture today. Is there any question before I go today? Is there any question?
Can you explain why you did 1 minus y instead of just 0 to 1?
Okay, that's a very good question. If I hear you clearly, you said, can I explain why I do 0 to 1 minus s instead of, 0 to 1? Take a look at this. Do you see what I circled? Now you are mixing chemical, and it's trying to say, okay, when you mix the two different chemical insecticide, okay, the total you can have is going to be 100%. You get what I mean? So when you take a look at x plus y, okay, less or equal to that, what is x? If you want to find x, subtract, when you subtract y from both sides, it's basically going to be this, right? If you do the same to y, it's going to be that. You see that? So we're putting into consideration this restriction. Let's say, if this is not given, of course, you're still going to use 0 to 1 here. But this is like a further restriction. Okay. And that was why we're trying to say, if I'm looking for f of x, okay, where I'm integrating with the respect to y, then the range is going to be from 0 to 1 minus x. If I'm looking for f of y, where I'm integrating with the respect to s, then the range is going to be from 0 to 1 minus y. Does that make sense to you now?
Yeah.
Okay. Is there any other question before I go today? Is there any other question? Okay, so in the absence of question, I basically want to thank everyone for attending my lecture today. Of course, I'm basically going to meet with you under the in-person, arrangement tomorrow. So I'm going to return to class tomorrow in person. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.